Welcome to episode 290 of CppCast, the first podcast for C++ developers by C++ developers. I'm your host, Rob Irving, joined by my co-host, Jason Turner. Jason, how you doing today?
I'm all right, Rob. How are you doing?
Doing okay. Do you want to talk about what happened at your house this week, or is that not worth mentioning?
Yeah, no, sure, why not? I had a little bit of excitement when I went to bathe my dog on this weekend. And at that moment, learned that in some of this very cold weather that we had, I ended up with a frozen pipe up here in the corner. And it's a thing that they do in cold regions, at least in the US. We've got these frost-proof silcock is what they call it. So when you turn off the water on the outside spigot, it actually has like this long pipe and it's part of the pipe. And it turns off the water back deep inside the house.
Right.
So if any water got trapped in that section of pipe that's more exposed to the cold air, then it might freeze, it might bust, it might do whatever, and you're not going to know it until you turn on the spigot, and then it's going to let water flow through now that busted piece of pipe. So that happened. And both my wife and myself were like, oh, it sounds a little weird, but Jason's just washing the dog, and I'm out there like, it sounds weird, and I only have half the water pressure I expect to have, but I'm sure it's fine. And then after a minute, I'm like, wait a minute. Oh, no.
So this was outside using the hose, and as soon as you went back in the house, you realized what had happened.
As I sprinted down to the basement as fast as I safely could, which is where I do my recording here. This is a basement. I have a nice bright window, but it is a basement. And discovered enough water to make us rush around very quickly and then try to find a professional who could make sure that it was repaired properly and all that stuff. It was exciting.
Yeah, sounds exciting. I'm glad it all got resolved.
I don't recommend it, just for the record.
No.
I also learned there's a phrase that basically doesn't exist in the English language. If you say a minor basement flood, right? Like that, those words, they can't go together. But
no.
It is pretty accurate what we had.
Any kind of water in the house is just not good, though. But I'm glad it was fairly minor. Yeah.
And no actual damage to anything. So
very good. Before we move on, one quick programming note I wanted to mention. PVS Studio's been working with us for a while as a sponsor. We really appreciate it. And one thing they asked us about doing a couple weeks ago and started putting together was generating episode transcripts. So they've put these out for a couple episodes now, and I've gone back and updated show notes for those episodes so that they have a link to the transcript, which is on PVS Studio's website, but they're making them in both English and Russian. So if you are a listener to the podcast and you think you might want to actually read through the transcript, or if you maybe know someone who might be interested but is deaf, or maybe just would prefer to read it versus listening to us, there are transcripts available for a couple episodes, and I think they'll keep making more of those, which we really appreciate.
And it can be handy just for like searching and referencing as well.
If
you want to be like, hey, I thought I heard someone say this thing at this one time, which right now is kind of possible if you go and look at the automatic transcriptions on the YouTube postings of these videos.
Right. But the automatic YouTube stuff is not, going to be
not
nearly as accurate. If I say CPP, they probably write out, the ocean, sea, something. They don't know what I'm talking about.
Who knows? Yeah. Before we move on too, Rob, we may as well talk about the fact that the view behind you has changed considerably as well.
Yeah, I don't recall if I mentioned it, but we are preparing to move. So right now we're getting ready to stage our house to have people come in and take pictures, and then do open houses for people to buy the house. So it's been a little chaotic around here too, but looking forward to the move. Yeah.
Good luck with that.
Yeah. Okay, well, at the top of every episode, I'd like to read a piece of feedback. We got this tweet from Martin Durham, and he wrote, Rob and Jason, hey, listening to your old new thing episode and heard you talking about lambda syntax. I 100% agree. We need an arrow syntax. I went so far as to implement it in Clang and wrote up a thing about it. Love your show. So he's got a link here, which I will put in the show notes. And the post is titled Hacking on Clang Surprisingly Easy. And I think he actually wrote a second tweet saying how, putting this type of thing in the compiler is actually really easy, but going through the process of standardizing it and trying to get it into a future version of C++ is a different story. But
I know there's been other proposals along this line, so there's certainly got to be someone Martin could collaborate with.
yeah, and this is definitely syntax that I've seen with lambdas and other programming languages, so I think it would make sense for us to get it adopted into C++ as well, this simpler syntax.
Yeah.
Okay, well, we'd love to hear your thoughts about the show. You can always reach out to us on Facebook, Twitter, or email us at feedback@cppcast.com. And don't forget to leave us a review on iTunes or subscribe on YouTube. Joining us today is Arnaud Desitter. Arnaud is a senior software engineer based in Oxford with 25 years experience in scientific programming. He has a special interest in software reliability and optimization. He holds a civil engineering master's from École de Pont, Paris Tech, France. He is a member of ACCU and has done several presentations at their conference and local events. He has worked on reservoir simulators for the last 15 years. He cycles to work, currently midway through his third virtual trip around the world. In his spare time, he sails an old wooden dinghy on the River Thames. Arnaud, welcome to the show.
Yeah, thanks for having me.
I'm curious how you ended up getting interested in scientific programming in the first place.
Well, I study civil engineering degree, and I got just a lot of lectures on mechanics, fluid mechanics, CFDs, and soil mechanics. And my first internship was about studying surfing waves and movement of sediment on the bottom of the sea. And I got really interested in the basically unraveled from then on. Right, I ended up being in Britain simulating groundwater flow at the University of Bristol, and then I found similar jobs ever since.
Well, that's pretty cool.
Yeah, very cool. All right. Well, Arnaud, we got a couple news articles to discuss. Feel free to comment on any of these, and we'll start talking more about the work and about that ACCU talk, or not ACCU, CP&C talk you gave a year ago, right?
Yeah.
Okay. So this first one is a blog post, Parameter Passing in C and C++. And I guess it's kind of like a deep dive in how parameter passing works in the assembly. Jason, you want to talk about this one?
Yeah, well, and specifically in the x86 64 that on Linux and Unix that we're used to seeing calling conventions. It references the System 5 AMD 64 ABI. But yeah, just like it's a deep dive into, how do these values actually get saved in registers and pushed onto the stack and everything when you're passing values between functions or in returning values. Actually, one comment in here is interesting. Is like, I actually, changed this code because the return parameter was uninteresting without me, complicating the example, basically.
Arnaud, you have any thoughts on this one?
Yeah, I think it was very interesting because my own guideline is always if your parameter is bigger in size as two words, which in 64-bit would be 2 times 64-bit, then you pass it by reference. And I'm kind of vindicated because that's exactly what the study shows, right? And as a matter of fact, I just look it up in the so-called core guidelines, and you got the F16 rules. Says indeed that their advice is 2 to 3 words, and it turns out on x64 then it's exactly 2 words. So in practice, which is why, for example, on a string view, you should pass it by value.
That's a good point. Yeah. Otherwise, you end up with basically a pointer to a pointer if you pass a string view by reference for no good reason. Yeah,
absolutely.
One of the things that really stood out to me, and this is the kind of thing I love to show students when I'm teaching, and I'm like, yeah, look, it's easy to see how the compiler's passing these parameters in Compiler Explorer or whatever. But I had never stopped to consider this example, make color. It's about halfway. Well, not halfway. It's towards the top, I guess. Make color and make color bad. And the author is showing the example of passing RGBA to a function, and then at some point swapping the argument. So it goes alpha RGB. And if you pass them straight through in the same order, then the compiler can do all kinds of optimizations because they're just going to stay in the same register no matter what. But if you swap just a little bit, then the compiler ends up having to copy all of the values around in the registers.
Well, I think one of the cool things is the around 2000-ish, when x64 was designed by AMD, they took a lot of care to redesign the argument passing. And I think they've done quite a good job, especially considering how bad it was before in x86. And with one of his decisions, you do once every decade, and he sticks for like 30, 40 years. And I'm glad they did it quite well, right?
Yeah.
It's an interesting comment. Like, I don't. Is anyone working on 128-bit calling conventions or anything? I haven't heard any discussion about that.
I doubt it. But maybe on the GPU space.
Seems like 64-bit should be able to stick around for a while.
64-bit should be enough for anyone.
I would think so as well.
Yeah. Okay. Next thing we have is it's another blog post. And this is on FireEye, and it is fuzzing image parsing in Windows, part 2 uninitialized memory. And I don't know. I might need you to talk me through this one, Jason. This is one you found.
Actually, one of my friends who watches my YouTube channel, but otherwise doesn't do any C or C++ development, but has been involved in security in one way or another for basically his entire career, sent this article to me. And he was like, I thought you might find this interesting. And I'm like, well, yes, heck yes, I do, actually. And it's just this cool exploration into how the author found use of uninitialized memory in Windows's image processors. And it's starting from the idea of fuzzing, which we've talked about fuzzing on here several times, but most tools can't detect a read of uninitialized memory. So one technique that's in here, which I had never seen or heard before, is actually running the same fuzz input multiple times and then detecting if you get the same output. And if you get a different output and one of the multiple runs that you made, then you know that you have a read of uninitialized memory somewhere that was undetected. So it's a whole deep dive into how techniques like that were used to find 2 different security vulnerabilities in Microsoft's image parsers.
Which I do believe they said, those vulnerabilities are getting patched, like Microsoft is accepting this issue.
Yeah, well, the CVEs were from 2020. So reading between the lines here, my friend who's been involved in security says that his opinion is that there's a good chance that these were actually submitted to Microsoft for a bug bounty and only released after Microsoft had fixed it.
Oh.
Yeah. When I read this article, what came to me is that's rightly so, the author said that Valgrind or something similar to Valgrind is not available on Windows, and I think that's maybe the crux of the matter on this kind of software, right? I remember very well Jill and Seward released Valgrind in March 2000, and I discovered it like 2 months later at the time. And where a software company was working, we actually, a colleague just took this very early version of Valgrind, and we found the software in production code straight away. And to me, it was like, wow. These new things, and say this thing is going to change everything, at least on Linux. And I think it did in a very large extent, right? So why Microsoft never invested to have it something similar on Windows, I am not so sure, but I think it's probably the way it is.
Well, yeah, there is a side comment in here that Dr. Memory, he's like, there are tools like Dr. Memory on Windows. And every time I've seen Dr. Memory come up, that's basically how it's treated. Oh yeah, well, and there is this Dr. Memory on Windows, but I've never seen anyone actually like give a report of how they used it and they found issues with it that they were able to fix. And I've tried to run Dr. Memory myself on Windows and have never gotten satisfying results from it. But it's supposed to be do the same things that Valgrind can do.
And the other fact I had was about the reference to LamCamToF, which is basically Michal Zalewski, and this guy is quite amazing, right? He's been producing American fuzz LOL on various similar fuzz technology for the last 20 years. And he looks like he must be responsible for able to find so many security vulnerability thanks to these ideas. And that's truly bewildering, right?
Yeah. Going back to the sanitizers for one moment, I did see that Microsoft announced that the latest version of Visual Studio, I think they're calling the address sanitizer, ready for production use, which is great to see. Hopefully they keep investing in that kind of tools, because I know there's like memory sanitizer too. It'd be nice to see that get into Visual Studio.
Yeah, memory sanitizer can catch that.
Yeah.
I think.
Well, I think memory sanitizer can catch it. My understanding or my recollection when I tried years ago is that you have to recompile every single application with memory sanitizer, which is very difficult for the third-party libraries. So in practice, usually people will use address sanitizer, and that's it, right?
Right.
That's Valgrind that used as a JIT doesn't have this limitation, but Valgrind has got a penalty which is easily 100 times slower, which usually you cannot afford, right?
Right.
Depending on what I do, usually we can't, right?
Yeah, I was recently using Valgrind to try to find an issue, and it was 20, 30, whatever times slower. And even on a relatively small test that took like 10 seconds, 10 seconds before I ran it through Valgrind, I'm sitting there going, all right, it's about time for this to be done now.
Yeah, I've got a few horror stories when we have to let it run for like 50, 60, 70 hours before finding the bug. And that's painful, right?
That's very painful.
Could be kind of fun to get one of our security researcher guests back on to discuss an issue like this.
Yeah. All right. And last thing we have is a post on Arthur Dwyer's blog. And this is, don't blindly prefer in-place back to pushback. And this is pointing out how some static analyzers will suggest using in-place back over pushback. But if you're not using in-place back the right way, then it's really doing the same thing as pushback, and as far as performance is concerned, but it's actually the compiler-generated code will take longer to do, which I don't think I was aware of that.
Like 3 levels of template instantiations to use in place back if you're not using it properly. Well, even if you are using it properly.
Right. So it's worth it if you're using it properly. But if you're not, if you're just doing substituting pushback with in place back, then you're not using it the right way. And it's definitely not worthwhile.
Yeah, if it was an interesting blog post. I use that exact same Clang tidy check, and if you use the fixit, I'm pretty sure it does the right thing.
Yeah, if you use the fixit, if you misread what the fixit said to do, then you end up doing the wrong thing. Yeah,
right.
But one advantage of in-place back in C++17 is that it gives you a reference to the last element, which actually can simplify a little bit your code, and sometimes readability is worth only for that reason.
Yeah, I think that's a really important point that should have been mentioned in this article as well.
Yeah, and the last thing that comes to my mind reading that article is about reducing compile time, and I've been on this odyssey for years trying to reduce this, stopping waiting and fighting sword with my colleagues while waiting for the build time, the build to complete. And the one nugget of information with GCC at least is that usually you might compile with -G to get debugging information. For example, to have a stack trace when you got a crash. And if you're not interested to use a debugger, you can move to -G1, and usually that cuts a third of your compilation time. So only that, if you pair your bill on the cloud, if you virtualize your build, it might decrease the money you pay every month by quite a bit, right?
So -G is equivalent to -GGDB. It's like full debugging information, right?
No, that's
and
right.
You're saying -G1, you're cutting it back?
So G1, basically, I've got far less debugging information. You still have enough to get you a stack trace where you crash, which is, if you do things in batch, is good enough.
Right.
The size of the object file is much smaller, so now if you need to debug interactively, that's not sufficient, but you can always do a special build at that moment.
Yeah, once you have the stack trace.
Yeah, okay. Valgrind works perfectly well in -G1, for example.
That is really interesting.
So there you go. That was my trick of the day.
I will accept that trick, and I wish I had brought my notebook down with me to write that down. Oh, I have a notebook computer in front of me. I guess that's related. Since we just mentioned decreasing build time in the context of in-place back, I accept Arthur's arguments that, it's slower to compile. I would be shocked if it's actually a problem. Maybe it is on some larger builds. But I was just recently working on some code, which I think our listeners will find this an interesting anecdote. So I guess I'll share real quick. About 30% of the total build time comes down to the fact that we're using a custom container where standard vector would have sufficed instead.
Is it a project you're working on? Wow.
Yes.
Were you able to make the substitution and get that increase in build performance?
I made a tiny wrapper class that uses vector in the background because there's a little bit of functionality that they added on.
Okay.
And it's probably would be relatively easy to swap out my tiny wrapper class with vector with just a little bit of thought for most of the use cases.
Wow.
30% of the entire project's build time.
That's crazy.
It is crazy.
All
So
right.
you do have tools, especially Clang has got a command line option to wiggle some feedback, and I think there's a project on GitHub whose name I can't remember, that allows you can do your build and then aggregate statistic to know where the time was spent in the inside your compiler at least.
Yeah,
So
that
after
is actually what I.
Yeah,
Sorry.
and at least on the software where I work, what you find is that you spend a lot of time compiling unique pointer, and I was thinking, well, that's actually rather good news because at least we are using it.
Right.
So we did find an outlier using Boost Azure was pulling an enormous amount of headers, and you can just put a macro, say Azure only or something like that, and it cuts something like 50 seconds of build time.
Wow.
But so that sounds very good, but it might be only 0.1% of your whole build anyway. So there you go.
That was so it's a -f time trace is the Clang flag, and I think Clang build analyzer is the tool that you're referring to.
Oh, it's really
yes,
good, right?
Yes, I used those tools to help me isolate those. Just for the record, I didn't just magically stare at the source code and say, clearly this is the slow part.
All right. So you did a talk at CppCast last year, I think, Arnaud, which was on the topic of improving performance by reducing memory allocations. Is that right?
Yeah, I did indeed, right? Yeah, I can talk a bit about where it comes from anyways.
Sure.
So as it turns out, I work for an old company called Schlumberger, and so I can say a few words about the company. It's an engineering company, a very large one, and we provide all services to all company. And one tiny portion, which is big in money but tiny for them, is producing simulation tools, right? So I work specifically on the Reservoir Simulator, which is the kind of software used to simulate oil and gas field. So we simulate the flow in porous medium. So that's as much as I want to say about the domain. Now it's not the topics of his podcast. And
Well, that's fine. People will enjoy it regardless. So go into whatever detail you want to.
So it's actually quite an important piece of software, right? I mean, a large amount of your energy you're consuming will be actually simulated by this kind of software or its predecessor. So it's definitely production software. But as a software engineer, what you end up is several million lines of C++ code for the simulation part, right? And you got the fact that simulation might last a few minutes on the laptop. It can actually keep a cluster of 1,000 processors busy for several days, depending on the size of the problem. So definitely reducing the time is a good thing to make the software faster. So that's one thing. And the thing we don't want is to change the results, right? So that's a big no-no. We can fix bugs, but we don't want to change the formulation. And one reason for that is that if you calculate how much oil you can produce, and you have a new version of the software, and you realize that now the numbers are different, usually people are not happy whatsoever, right?
Right.
So we have to be very careful. So in other words, if I fix something, the last thing I want is to break things. I just want to keep the result identical. So to come back to the reducing memory allocation, I mean, a large part of it comes just looking at the source code. And as a C++ developer, you've been brainwashed by the literature, like Scott Myers and so on, and say, memory allocation is really, really bad. You should reduce at any cost. The fact is that I never found a tool up to semi-recently that tells me where this allocation take place. So you see a lot of micro benchmarks, but when you take something which is very big, finding this allocation and the one that actually matters is actually quite difficult. So what you can do is you can do some profiling with whatever technology you want, VTune or Perf. And usually what you find for most C++ code base is about 5-10%, let's say 5% of the time is spent inside the heap algorithm. So we spend in malloc and free. So intuitively you think, well, actually, if I decrease half of my allocation, I might gain something like 2.5%, which is quite frankly not worth it, right? It's not a lot.
Right.
So that was it, right? On the and then in 2016 we got the customer contacted us saying he was very unhappy because now his simulation was 20% slower with the new version of the simulator than the previous version, which is something which not very desirable. So we actually backtracked inside the vision control system and we traced it back to an upgrade of CMake, which is rather counterintuitive. We say, how could CMake reduce an HPC or an high performance computing application by performance by 20%? That makes no sense whatsoever. And what was even more curious is taking the head of the tree. The bug has actually disappeared, but we didn't know why. So clearly something happened. So a colleague called John Herring did some detective work and managed to crack it. So kudos to him, right? And so he actually did try a lot of things, and he finally attached the process with VTune and managed to trace to find the root cause, and it goes that way, which is you could see that somebody by mistakes introduced a copy of a small vector, a vector that contains something like 5 or 6 elements as an int actually. So it was a stud vector of int, and he introduced a copy in a critical loop. So basically, we started copying these 5 or 6 element and copying the vector again and again and again, millions or billions of times. But that by itself shouldn't be a problem. What was really, surely that has nothing to do with CMake. But what happened is the new version of CMake basically changed the order of the linking. And somewhere when you do the link, the specific instantiation of stud vector of int has to be picked up from somewhere, and only one is kept at link time. And this one was picked up from a third-party library that we link statically in our application. And sadly, it was actually compiled without optimization on. So what we did is that stud vector for the copy constructor of the stud vector was actually used completely unoptimized, right? So we amplified that copies by a gigantic factor, and we ended up taking 20% of the simulation that might take something like 10 hours. So, and what happened in the head of the tree is that we did some profiling, and we actually found that problem, and actually I did found it, but I didn't even remember it, so I fixed it and moved on, right? So anyway, that's a nice little story. What it tells you is that, well, first of all, you should be quite careful when you compile your third-party library. And I think we learn our lessons now that is now fully automated with Clang, so we don't have that issue anymore. But the other thing is that, okay, so I got 20%, but maybe once you fix the optimization problem, it will cost you, let's say, 0.25%. But what about if I've got many more of these copies, which I'm not aware of? How much do they add up? And I didn't have an answer to that, right? I even considered recompiling the whole simulator, changing libst C++, and make the copy constructor very slow indeed to find the origin of all these things. I say that's not very practical, and I don't have the time for that. So that was it, right? And the end of the follow-up to the story is that I went to the SCCU conference in Bristol in 2017, and I attended John Lakos' talks, or one of the many talks by John Lakos. So John Lakos at Bloomberg is Mr. Allocator. He's been selling allocators for years. I remember attending his talk, which was truly fascinating. I think I don't even know where my allocations are. So let's alone trying to replace them by a specific allocator. And that was it. So I left the session at the end of the session, and I talked with a friend called Matthias Schulz, which was attending the conference. And I say, well, I wish I had a tool. And I say, well, why don't you use heaptrack? I say heaptrack. I never heard of that. So he opened his laptop and started showing me straight away heaptrack, and he had this amazing ability of capturing at a very fast rate. Pretty much like Valgrind is you put heaptrack in front of your command line application, and then you basically log every single of your allocation from malloc and free. And then you can just go to GUI to later on, basically to display all these allocation with flame chart and very nice GUI capability. I was like, well, this is it, right? One of these Valgrind moments, right? I mean, suddenly I've got a tool where I can work with, right? And so that's really the start of the talk I gave 3 years later was really in a way to give back to the community what I learned thanks to this amazing open source tool. So
right. So I don't think, we've talked about lots of different tools on the show, but I don't think we've ever talked about heaptrack, right, Jason?
I don't know. It was, I think the first time I saw heaptrack, it was in one of the poster sessions at CppCon, like in 2017 or 20, maybe that might be right. 2017 sounds like the right ballpark for what you're saying too. But I've never used it before myself. I feel like it's possible we may have mentioned it because of a lightning talk or something,
Or
but I don't know.
Link,
I don't know. Yeah.
Certainly never gone in depth on it.
No, we haven't.
So heaptrack is the author is called Millian Wolf, is a German software engineer that works for KDAB, and he done, well, in my opinion, an amazing job. And when you look at his, when you watch his videos, or say, "Oh, I'm standing on shoulder of giant," I was thinking, well, that's pretty good going. You've done quite an amazing job. So what this tool is doing is basically capturing the stack trace and then use something called lead backtrace, which is part of GCC. To symbolize the stack traces, but it does it in a queue, so the slowdown is actually very acceptable. So as long as your application doesn't call basically malloc and free at an extremely fast rate, the override might end up being very, very small indeed, right? And then you can analyze and find out where they are and start to mix to trying to fix it, right? So so if you watch the talk I gave at CPP on C, which was online, it was really the tale of, first of all, how can you install it? And it turns out that, again, Millian Wolf made it very straightforward indeed, right? Because you use a technology called app image, which basically you just wget a blob and make it executable off you fly, right? So that's very, very straightforward to try. But then, so I try on the simulator, and what I found is well, it was not very pretty. It was totally unexpected to me. I mean, we had a runaway allocation inside of the inner loop, another one. So I went, and one of them was basically copying a vector and never ever using it, right? And when that's probably a debugging experiment that was basically a leftover. But if you think about it's a kind of tragedy of C++. If you put a stud vector, you put 20 elements in it. It's actually for the compiler, it's an unused variable, but not as far as the compiler is concerned, because it's got side effects. So you got no warning whatsoever. So that was easy to fix. I just removed the piece of code, and I had a 2% speed up. And I said, wow, okay. And
you should have, instead you could have put a comment comment this, remove this line when we need more performance.
Yeah. So I ended up in this after month of works and chasing up one after the other all the problem I was seeing, at least on the common code pipe, and I indeed reduced it by a factor of 2 order of magnitude, right? So when we had something like allocating 500 millions, now we're under 101 millions of allocations. And if we go back to the story, that would consume only 5% of our time. My surprise is that, at least in serial, the speed up was more like 20%. So that doesn't quite make sense. And the reason for that is when you look at the profiling, the time spent in malloc and free is indeed something you pay for. But what it does is destroying all your caches.
Okay.
So actually, it's really hard to estimate what this allocation cost you, because it could be that it's in a relatively cold loop or something when your cache behavior wasn't great anyway. So that's cost you the cost of malloc and free. But if you're in a potentially hot loop, it costs you far more than that. It costs you the fact that basically you don't use memory efficiently anymore. Your cache hierarchy is being is being destroyed by going out of line and so on and so forth. So potentially you got on much more to gain by actually fixing this issue.
So when you
go for it.
when you run heaptrack, you said you basically run it like Valgrind, like it's heaptrack and then your executable.
That's
Is
right.
it? And you make it sound like it's just that straightforward. You pull up the interface or whatever after it's done and go, oh, well, look at that, line 12. I should probably take a look at line 12 because it's doing way
that's
more.
much it. Absolutely. So what you say heaptrack, the command line utility, it will leave your application working as normal, right? And when you stop the application, it basically write a file, compress file containing all the information. And then you have good GUI that comes with heaptrack, which you can install very easily because it's pre-compiled on Linux. Oh, I forgot to say, all this is Linux only.
Okay.
You can basically read this file and analyze this file. And the most useful part is to use flame charts. So I don't know if you're clear what a flame chart is.
I don't think we've ever talked about it on the show, but
No.
I'm familiar with it from Chrome's tracing.
Absolutely. So you got this enormous quantity of data to wait through. And flame chart makes it quite easy because you're going to display, if you're interested in the number of allocations, that would be 100% of them will be on the X's, and on Y you put the stack traces. And then what you care is about this big rectangle or this, you want to reduce basically the one that becomes very frequent, right? Or the allocation which are repeated inside the loop, and that's the first one you want to target.
Right.
And so you go, trying to do something about it, and if you succeed, you just repeat the experiment and see if this thing has improved things, right? And rinse and repeat thousands of times until you get it sorted, right? So yeah, to me, heaptrack is an amazing technology in that respect, right? I mean, I'm quite surprised that people don't use it more often. And one reason I did that talk was to make it more popular, or hope so anyway.
I've got a bunch of questions right now, but the first one that I would like to ask is, you started this story by saying that you were in one of John Lakos's talks and you're like, oh, allocators, clearly that's our answer. Then you came over to heaptrack. I'm curious if you ever came back to allocators and said, well, okay, there's still these things left that I wasn't able to remove, so I'm going to use allocators here, or if heaptrack just got you all of the help that you needed.
Well, so again, referring to my own talk, that was what I try to do is to categorize all, first of all, what I found as, I'm not saying that the application I work on is necessarily that typical, but it is written by a lot of people over the years. You got 20 years of development by a team of 20 to 40 people constantly, right, with a lot of churn. So you will expect probably have something quite typical. And is there allocator useful, or what in C++17 is PMR allocator? And the answer is yes, right? I would say that is actually at the back of the list, right?
Okay.
It's actually much simpler techniques to deploy first before you get to use allocators. And I can elaborate on that if you're interested, or
yeah, go ahead. Yeah,
sure.
Yeah. So the where allocators is useful is specifically for associative container.
Okay.
So a usual case is to have basically you got an unordered map, or a map if you're unlucky. And the typical thing is that you're going to populate it, but you never remove any element. And once it's populated, it becomes kind of immutable, and then you keep on doing a lot of lookup.
Mm-hmm.
So because it's a node-based allocator, if you put a map containing 2 million elements, and that's very frequent in what I work on, you end up with 2 million allocations. So if your problem is of size 10 million, you might do something like 50 times these 10 millions. And that's the map which is populated only once is a poster child, basically, to use a motoring buffer resource.
Right.
You put a motoring buffer resource associated with that map, fill everything in, it will probably reduce to something like 30 allocation due to the amortized growth. And you basically, it works beautifully, right? As long as you don't copy the map around. So you have to be very careful of that. So you presumably it's inside an object that should be made non-copyable, right? And that works really, really well. Another use of well, a use of the allocator which I found quite useful is a typical situation when you got a lot of, at least you do that in a lot of numerical application. You have a lot of vectors, which size you know. So you might actually have, if you got physics, you might have something like number of components, and you got 20 vectors with different names. But you don't know how many components you will have, but it will be something quite small, right? And so you end up vector 1 of size n, vector 2 of size n, vector 3 of size n, and you allocate that inside the kernel. And they all add up for something like 2 kilobytes of memory or something like that. So again, because you know the size at runtime, it doesn't move, you can put a monotonic buffer allocator, resource, pardon. You put 2 kilobytes of memory on the stack, which basically is passed to your memory buffer resource. And then the only thing you have to do is to transform your vectors into PMR vectors and associate that resource, and that job done, right?
Right. And you saw a significant impact making that kind of change?
Well, again, it depends what you put significant, but yes, in production, I will gain 1% here and there on speed. If you consider a major,
adds up.
Yeah.
Well, if you take an extremely optimized major industrial system and you speed it up by 10% on any case, that's pretty good going, right?
Yeah, that's definitely good.
Well, it's the same thing is that you well, first of all, this kind of software I'm talking about is will be used on clusters and keep them busy and warm for a long time. So if you can decrease your electricity bill by 10%, that's quite a good thing. And I think it's a good thing for the environment, which, and in any circumstance, right? And it's just better use of of resources.
Right.
But having said that, I think all these PMR facilities is probably the last thing you should do, right? Is they are actually usually much easier techniques to deploy, right?
Okay.
And,
just eliminating the dynamic allocations in the first place.
Well, the poster child for that would be like, unsurprisingly, in C++, you will find that you spend a lot of time copying strings around.
Right.
So the first thing to do is probably to use string view when you can. So a typical one, you might do some parsing and use sub-str, which create a new string, only for the benefit of parsing. If you actually make it a string view, you end up with something very lightweight that's got 0 allocation. So that's a solution to a lot of problems. And the other one, which is very interesting, is C++20 span.
Right.
And the reason for that is that in a lot of numerical simulation, you end up passing, you want to pass a lot of vectors. So usually the way people code in C++ quite naively is to pass a reference to a vector. And there's not really a problem with that. It's just, well, first of all, if you pass a reference to a vector, you never know if the function you're calling is going to resize your vector. In my outing, whereas if you pass a span of double, you know that it can't possibly resize that span, right? You can only populate it. But the beauty of it now is that you, so first of all, by doing that, you make your function more strict in terms of contract. You clarify that you're not going to resize that vector.
Interesting point, yeah.
So that's one thing. But the other thing is that imagine now that your physical problem is to pass a vector of size 2, which might be, for example, oil and gas, a number of phases.
Right.
If you make it a vector, you're obliged to allocate a vector of size 2, which is a bit silly, really.
Right.
And that can go on the stack. So if you make it a stud array of double, 2, and the function you're passing to is coded in terms of span, then you don't force the allocation scheme on the color, right? You can tell, or the color of the function can actually use any kind of contiguous container. That could be vector, but it could be array, or it could be a small vector implementation, which I've been using extensively. And in a lot of situations, your vector might be on a relatively small size, and small vector is the way to go, right? Or you might want to use PMR vector.
Right.
And well, I think to me, span was really one of the very, very useful addition of C++20.
We need to talk about how you are already using C++20, but if you don't mind, I have one other question about your heap track and So you commented that standard string, having lots of copies of strings is pretty typical of a problem in C++, which I fully agree with. I'm not going to argue with that at all. But does heaptrack, now if I have a bunch of small copies of strings spread across 200 functions, does heaptrack help me say, at least point out, hey, you're copying string in far too many places, and it's going to be up to you to dig into where? Like, is there any way to bubble that kind of information up?
No, absolutely. You so you use the flame chart. Usually, what I do is that you use the reverse flame chart by putting the leaf at the bottom. So you can now search for the copy constructor for string, and you can see where they come from. But the beauty of the flame chart is that maybe you don't have this problem. So you can see how many allocations take place, right? So if it actually occupies only 0.1% of all your allocation, your problem is elsewhere, and you shouldn't waste time on that, right?
Right. Very good.
So actually, it's very efficient. Having said that, the other thing is, imagine if you take the example of JavaScript, for example, your program. Depending on what you parse, you will see that the allocation will take place in different places, right?
Yeah.
So what I'm trying to say here is what you do is you optimize a particular code path depending on the workflow. If you in my case, in terms of simulation, if I take a different field or different type of physics, it will go in different places.
Right.
And then, of course, now your distribution of allocation will change.
Yeah, these kind of scripting and simulation environments are difficult to profile, because you have to try all the possible different code paths that someone might do and choose what you're optimizing. And
well, the danger there is to say, because I can't do everything, I do nothing. And
right.
What you can do is take a few typical cases and having a good go, right? And usually that can make a big difference.
So do you have any now techniques or automated process of any kind to be able to run heaptrack and say, okay, nothing new and scary has now popped up? Like, is there any way to do this in your CI or something like that, just to give you like a sanity check?
Can you do it? Yes, absolutely, because it's a batch application. So heaptrack will basically give you how many allocation take place, and then you can just put a threshold and say, well, now
just look at total allocations or something.
Yeah, at the end.
Okay.
So it was very easy. We have not implemented that, but we could.
That's a really interesting idea.
That's very easy to automate, right? Now the question is, how many things do you track down in your CI? That's the other matter. That's the other question, right? So typically on what I work on is that if I put any modification, there's 3 hours of test before actually the pull request can be accepted. So we run a lot of tests, a lot of unit tests, and we run a lot of them on the address sanitizer and this and that. And at some point you have to decide where the limit is, right?
Right.
And that is only the first level of testing. So but you could absolutely automate to some extent the fact that you don't actually re-inject an enormous number of allocation.
Right. So you made some references to using C++20 already. How are you on the bleeding edge of the standard?
So maybe I slightly overstated this.
Okay.
So what you can do in C++, no, we do not use C++20 or I do not use C++20. What I do use is span specifically, right? So so what I needed a span, and so what I looked around, and there is many people that coded a span. So it turns out that the standardization process, I was thinking, gosh, I got this good feeling that span is going to be successful, and there is a fair amount of implementation. So there is one in GSL, which I used to start with, and these days we use the implementation by Tristan Brindle, which is really excellent. It's just a single file. Okay. So you put it inside your project and you call it, I don't know, SSS span or something like that in different namespace, hopefully 3 letters, and then you can just change it to STD next time around, right? Which is exactly what I did for string view in 2016. I imported a string view implementation written by Marshall Crowe. Okay. And only something like 4 weeks ago, I changed everything to STD string view once for all. But it gets off a 4 years ahead of the curve to be able to use string view way before everybody else.
Nice. So you are able to keep using new versions of standard, though. So you are on C++17 then?
Yes, we are, right. So as far as I can make it, C++ was kind of vegetating a bit, and people have been slow at adopting C++11. And we finally got the go ahead in 2015 on the project I work on, and I went slightly crazy, right? So we basically changed the code base or put as many features as I could. Well, no, not as many. I mean, useful features as I could at the time. And so the first thing I did at the time was to very aggressively removing all the naked new and delete.
Right.
And when I counted, I had about 3,000 naked delete, and I reduced it to under 100, so that was pretty good going. And that was done manually.
Just to make unique, you're saying? Or, yeah.
Yeah, just to a unique pointer or
Right.
whatever was necessary. But otherwise, Clang tidy was actually the way to go, or is the way to go these days, right? So, and incredibly, it's very, very reliable. Well, there's two things. First of all, a lot of transforms are reliable. So I did blankly transform on several million lines of code. And the other thing is when I did find bugs in Clang tidy, usually they fix the bug within a few days. So it's actually
Nice.
well worth filling a bug with both Clang and both GCC, actually. So I got many bugs I found in GCC got fixed in a matter of hours. So they are always quite amazing, these guys.
So what's the process like? Are you still then, you said you did your first thing to do is to remove a bunch of manual news and deletes, but are you then able to keep upgrading? You said you're on C++17 now, I believe. Did I hear that correctly?
Yeah, so the process would be, well, C++ 11 and 14 is well consumed. C++ 17 string view, for example, was very useful. Another nugget information for you, but you can refer to my talk, is if you use a PMR map and you insert element in it, it's actually a very, very bad idea. And the reason for that is when you insert on a map, it creates a temporary node, which might be inserted, but it might be actually discarded. And if you use a monotonic buffer resource, you end up with a slow memory growth.
Okay.
So the trick there is to use try and place, which is C++17, which basically guarantees you not to have temporary nodes and avoid that slow memory growth again. So that's another example of C++17. And I think a large part of all these transforms were more political than technical in essence. I mean, to me, the reason why you will remove manual memory allocation is first of all to remove bugs, but it's as well to make the project more attractive for new people. And in a way, we've been very successful in that, because I had people that came in the project since, right? And I say, oh yeah, we use a lot of memory, but we know we don't have memory leaks because we only use smart pointer. I was like, yes, we won the battle. So I think there's a large aspect that if you're a young graduate, the last thing you want is to work on the whole code base, which is in a terrible state, right? So if you got something which is more palatable or kept to a higher standard, it makes the project far more interesting.
That is really a fascinating point. I haven't interviewed for a regular job in quite some time, but yeah, I mean, if they said we're working on this great code base that's so much fun, and then you find out later that it's nothing but a bunch of manual memory management, you're not gonna. It'll be a shock, right? Using it as a way to recruit people to say, no, we're actually making the best advantage we can of modern techniques. That sounds.
Yeah. So the talk I gave, its origin was as well that I had to convince my colleague of the usefulness of this technique. So I did a lot of internal talks. So I had to write a lot of slides and convince them, bouncing up and down, showing how great all these things were. And because I had all these slides, I reshuffled them and gave it to a conference.
It's a great way to do it.
Exactly. So maybe some homework for you, Jason. You can do an episode of your YouTube Cpp Weekly on heaptrack.
Nope. Yeah, I might do that. Yeah, I feel actually you're making me feel bad, honestly, because like I said, I know I was made aware of this a long time ago at CppCon, and I've never tried it.
Definitely sounds like a really useful tool.
Yeah, and
Yeah,
considering I pride myself in being like the use all the tools guy, and this is like an easy to use one, and I've never used it, then I just feel bad now.
Well, I'm surprised that people don't use it more regularly or aware of it, but maybe the reality is that there are so many new things happening and so many things to know, but there is only so much things you can learn, right?
Yeah, and there's a certain level of like awareness, right? Like at this point, quote, everyone knows about the sanitizers. So saying, oh, I'm going to deploy the sanitizers in this project, most people aren't going to argue with that, or Valgrind or whatever. People have used these things, but you have to like take this to your coworkers and be like, oh, by the way, I ran heaptrack on Monday morning because it seemed like it would be fun, and I got a 3% performance improvement in 10 minutes. Then people are going to notice, right? Like, yeah. So I might have to.
Yeah, no, it's or maybe you can just I can only recommend it, basically, right?
Yeah, I have an idea. We'll see how it plays out. Thank you very much for sharing this with us.
Yeah.
So there you go.
Okay. Well, Arnaud, is there anything else you want to plug since we're starting to run out of time? Anything else you want to go over?
No, not really. I want to thank you for inviting me. I mean, you said in my bio that I'm cycling to work. So a few years ago, I discovered that the cycling on the ice was a rather bad idea. So I had to basically replace my cycling to work by a long walk to the station, taking the train, taking the bus, because I couldn't cycle, and because of a small accident I had, and and I was able basically give me a lot of time to listen to all your backlog of CppCast. So I had to thank you to make that period of my life much more enjoyable. I went for something like 50 or 60 episodes now.
Wow. Well, I'm glad that was helpful.
Yeah, definitely.
So there you go. And I think a lot of colleagues I know of is listening carefully or regularly to your blog, and it makes it very interesting.
Thank you.
Yeah. Okay. Well, Arnaud, it was great having you on the show today.
Thank you very much for having me.
Thanks for coming on.